I'm going to talk about two things today. The one is MFBox is a multi-fidelity and multi-scale emulator, and the other thing is the PRIYA simulation suite is a Gaussian formation suite based on Astrid simulation model. Let me start with this talk by asking, when we are running simulations, if we want more small scales, what do we do? What do we do in this situation? For example, when I just started, I didn't realize if I just looking at this simulation box, it doesn't mean anything at small scales. Because when you get into smaller region, you can see this one actually lacking of the structures at small scale, even though I just running like 10 times of the region. So I asked simulators what to do. So the answer I always get, just increase the resolutions. What does that mean is that more particles or denser grids, which you don't see any difference at large scales, but as the smaller scales, you have more structures. One thing confused me at first is that I'm wasting money on running higher resolution to get exactly the same large scale information. The other thing is that I need to be cautious about this because when I increase the resolution in this way, the computational cost is proportional to roughly n log n, which means here, if I increase 64 times more resolution here, it actually translates into roughly 100 times more computation time. So the problem we are facing is that the cost of running higher resolution simulations increase dramatically with the number of particles or number of grids, but we get almost the same large scale information. So the way I answer this question is we had a paper out last year on using multi-fidelity method for the matter power spectrum, where the idea is that I have the accurate information from the high fidelity. I only use a few of them. But I have inaccurate chip simulation, which has the same information at the large scale. So I use tons of them to understand how large scale statistics vary with different cosmologies, and use just a few high fidelity to refine my information at a small scale. So in this way, you get the lower cost and also lower error. It turns out that's not usually what simulators do or think. They take a shortcut. So at some point, I realized they are just lying to me. Increased resolution is not the usual practice. Inside their brain, they can do the kind of separate scales for different physics. What do I mean by that? If I ask the physics at large scale correct, simulators will just run the large volume, low quality simulation, a test run. For example, checking large scale matching to the linear theory. And to check this small scale subgrid model correct, just run a small volume, low quality simulation and evaluate the small scale statistics. For example, we can tune the supernova stellar wind model in this way. And sometimes it's not just about no money to run the simulation. It's much better to run the quick test simulation so the development can go much faster if you want to check, for example, the implemented physics is correct or not. But my question is how to turn or how to integrate this thought process into a more coherent way to do either the emulator or the future decision making. So we will have a similar plot as our previous speed and accuracy plot, but this time the small and large scales. So we are assuming we have a perfect high-res large volume simulation. Comparing to this, we have low quality L1 simulation in large box, low quality small volume simulation L2. You can see L1 lacking small scales and L2 lacking large scales because it's small volume. Our attempt to address this question is a method called the MFBox. It's multi-fidelity plus multi-scale emulation scheme. We combine different scales into one Bayesian model. So it's kind of just an extension to the idea of multi-fidelity, but we include the scales information. So on the left-hand side, L1 large box, L2 small box, low qualities, pairing this information with the high-quality large box simulations. And right-hand side, you can see the L1 lacking small scales, L2 has small scales. And you combine the scale separation, pairing with the high fidelity. And it's not just about fidelity and scale, it's also about emulation. So we also varied the cosmologies or vary also the input parameters. So here I just show varying different cosmologies. L1 and L2 are chip simulations, expensive simulations here on the right hand side. So note that because we also need to balance in the speed and accuracy, we can only run the few expensive simulation here. And how to select the expensive simulation? We did a trick by using a so-called sliced Latin hypercube design is a clever way to select the high-fidelity simulation set to maximize the information. Why we do this is that although we have tons of chip simulations, we still need a few expensive runs to refine the information. The slice Latin hypercube help you to have a subset. For example, the dots here are from Latin hypercubes, and the diamonds and stars here are two slices from two subsets. You can see from the stars here, it's trying to maximize in the minimum distances between the points, which will translate into maximizing the diversity within a subset. And I just plot the three simulations here from the slice 0 here. So what does the Multi-Fidelity Emulator and MFBox do is doing the probabilistic resolution correction using Gaussian processes. So just comparing between the previous multi-fidelity method we had and to the current method we had here. The previous method only works for different particle loads from low to high. So theta here is the input parameters. You can imagine it's just cosmologies. And F here is summer statistics, assumed to be power spectrum. So what the multi-fidelity method is doing is finding the cosmological dependent resolution correction function. And what MFBox does is you have additional smaller box information. But currently, it only works for summer statistics because GP only takes small data set. But the nice thing about using GP is that it almost requires no tuning time, almost minimum. When I do this, it's almost effortless. I just click the button and everything just trained without any tuning. It also works as a decision-making tool for either optimizing the budget for building an emulator or optimizing the budget for running a simulation campaign. So here just a toy example showing if you have an objective, for example, maximize the accuracy of the predicted summary statistics and have an empirical error relations, kind of error decreases number of simulations here. Subject to a limited budget, that's the budget for L1, L2, and high-fidelities should be smaller than my limited budget. So just back to your kind of undergrad classical mechanics, just solving the Lagrangian and also solving under the KKT conditions. What you will get is this relationship. Number of simulations per node should be proportional to the correlations of this node to the high fidelity, to the correct information, and inverse proportional to the cost of this node. So it's very intuitive. It's just simply saying number of simulation per node is proportional to how correct this node is divided by cost. Just show you that empirically this relation works in general. So here I just showing different number of high fidelity and vary the arrows as number of low fidelity simulations. Just take the first one and the final one. The arrow of the summary statistics decrease when you have more low fidelity simulations. If you change the number of high fidelity, you shift this relation to lower. Roughly follows a power law. So with the empirical error relationship, going back to the solving Lagrangians, and we get optimal budget allocation line here in the green dotted line corresponding to the optimal budget allocation. An error as a function of budget size. Here I plot it in the units of cost of line L1 simulation. So basically saying how limits of your simulation runs, how accurate you can get. So it's kind of naive estimation if you assume the empirical relationship you infer is correct for all of the future runs. If you don't follow the optimal budget, then you will have the solid lines here. If you only increase the low fidelity, the dashed lines, you only increase the high fidelity, you won't get optimal results. You need to vary both the number of simulations corresponding to different scales and also corresponding to different resolutions. That's the way you get optimal results. MFBox method. The best way to see the performance is how to see how it works on combining scales. So in general, 2 boxes works better than 1 box. And when you are decreasing using a smaller box size in one of the low fidelity node, you in general getting more accuracy by using smaller box. And in the k-space, you see the most difference happen as the small scales. So another interesting feature I think in the MFBox is that we can leverage the accurate information from L2 to improve or cancel out the systematics in the L1. If you think about that, because you're running low quality simulations, which means that there might be some systematics. So this is a good demo here. If we look at the L1 power spectrum and the registry here, we have the power spectrum arrow kind of shooting up more than 20% at the scales in the squares. This is due to the initial interparticle spacing in the our embodied simulations. Because it's too low quality that the nonlinear growth cannot wash out the interparticle spacing at this scale, which translated into the emulation that we can see for one box size example here. You have low systematics in these scales, although it's like 10% in these scales, which means the multi-fidelity method kind of improve into 10%. But if you use two box sizes, that you have information from L2, which has less systematics compared to the L1. So you have more accurate information onto more small scales, which translated into the MFBox emulation have more accurate, like below 1% onto certain scale. So the non-shared systematics could be cancelled out, but the shared systematic will be still there. If you think about that, is for the L2, you still have some initial interparticle spacing at smaller scales compared to the L1, but they are there. So this is kind of a good demo here that you see if they are shared systematics, you have hard time canceling this. But in general, it's kind of interesting feature that you can play around with using different informations in the low-fidelity nodes to cancel out the systematics from each other. Here we present PRIYA simulation suite, which is a galaxy formation simulation suite that we ran based on the Astrid simulation model. The primary purpose for this simulation suite is for the Lemma forest studies. In the PRIYA simulation, we have two different resolutions. Since this is a galaxy formation simulation suite, we include supernova feedback, black hole feedback, reionizations, including both hydrogen and helium. So one special thing about Astrid simulation model is that we have dynamical friction for the black holes, which give you more physical trajectory of the black holes in large volume cosmological simulations compared to other simulations usually use repositions of the black holes. So in our PRIYA simulation, we have a realistic population of DOAs, damp Lemma absorbers. It's important to have LAM because they are known to be contamination of the 1D flux. Here we plot all of the DOAs in our simulation. So those are high condensancy systems. And we compare with the whole 2021 is a condensancy distribution function from the SDS SDR16. They match quite well. So this is also one of the reasons we fixed the supernova feedback, because DOAs are the tracers of low mass halos, which also associated with the supernova feedback. So that also means that for those simulations, we don't mask out the DOAs in the sidelines. They need to marginalize over the subgrid of the supernova wave model to get a correct inference result. And the plot here is showing we have very dense sidelines that plotting in the grids in 3 different dimensions. And it's so dense that we can plot into 2D. You can just directly see the structures. Right hand side, we show high-res, low-res simulations that looks similar on large scales, but if I plot just one sideline, the transmitted flux actually looks different. So here, we kind of zoom in into a smaller region to see what's the actual difference between low and high fidelity simulation suites in PRIYA. So you can actually see the subtle differences as these scales have finer structure as the HF1 compared to the low quality one, which translate into a 1D flux difference as roughly 10 to 20%. And we use the multi-fidelity method without an MFBox and corrects the resolution up to 1%. So here we show the 1D flux power spectrum predicted by the emulator trained on PRIYA. So here, the variations of the 1D flux includes the astrophysical feedback and also reionization. So the left-hand side, we show just one cosmological parameter variation that The IP is the amplitude of the initial Paul spectrum at a certain scale. The second one, agent feedback, is this effect is very small, it's kind of below 1%, but we need to clarify that this is not the effect with or without agent feedback, but rather this is the effect that controlling the feedback parameters in the black hole. So this parameter here is generally saying how much the black hole accretion should hit the surrounding gas. So lower the values, then lower energy will deposit to the gas. So there will be more black hole accretion. And the third one, we have hydrogen patchy reionization. So the Z redshift hydrogen reionization here is the redshift of the 50% of the reionization happen. And after reionizations, then the temperature will be boosted to the 15,000 Kelvin here. Why it affects the 1D flux is because the temperature will basically change the neutral fraction of the IgM, and those change the amplitude of the 1D flux. And finally, we have this inhomogeneous helium-2 reionization. So the idea is that you have these bubbles of the helium-2 reionization assigned to the halos and assuming to be a quasar. And it just hit the surrounding gas. Alpha Q, the parameter here, is the spectral index of the quasar radiation field inside the bubble. And we vary these kind of subgrid parameters in a range. As you can see, there's a scale-dependent feature because at large scale, it's kind of correlated with the buckle size of the reionization. So in conclusion, we presented two things, MFBox and PRIYA simulation suite. But MFBox is a multi-fidelity and multi-scale tool that helps you to combine resolution, scale, and input parameters into just one basic model. And it also helps you to optimize the budget allocation. So it works as a decision-making tool to predict future budgets, and it also helps you to write proposals. How much time, how much money I need to run this simulation campaign to get optimal results. And we also present PRIYA as a multi-resolution DLC formation simulation suite, primarily for the laboratory studies. We also built a kind of big, large volume emulator, various cosmological effects, including Gaussian reionization, inhomogeneous reionization, and also various cosmologies. So all we present here kind of shows multi-fidelity and MFBox method can kind of go beyond just being cosmic emulator. It can serve as a surrogate for galaxy formation simulations. Variations from the subgrids also include those. So finally, chat with us if you are interested in our simulations or interested in the method. Thank you for watching until the end. Hope to see you in the conference.